Hello everyone and welcome to this new episode for the STM32 tutorial. And today we are continuing our chapter regarding the STM32 clocks and how to change with them. And this chapter is the most interesting one where we really understand how to unleash the beast and change the clock, give like the maximum clock of our STM32. So by the end of the chapter, you will be understanding exactly how to do this in whatever the microcontroller you are using. So for today, we are changing our microcontroller using a different one from the previous video, just to show you the modularity of the code that we are going to build. And as you can see here, and this is what we are going to do at the end of the chapter, we do have the clock of our microcontroller or the system clock as a 16 megahertz, and this is the by default that is generated when you get your code. And now by uploading the code, the new code, our microcontroller speed is around 168 megahertz. So it's a 10x, more than a 10x speed increase. This is within the spec of the microcontroller, and this is something that we'll learn to do not only for our microcontroller today, but also for whatever the microcontroller you do have. So to give you a little bit of perspective regarding this chapter is coming as the chapter number 3, and as we said, this is where we unleash the beast of the microcontroller. And after that, we will have another very important chapter to know with a great responsibilities, with a great change of the clock. There is some other parameters that we need to understand so we don't mess up with our further operation that we will have. Okay, so from this tutorial perspective or the tutorial topics, first of all, we will see again if we do have a different microcontroller to the code, because this code is available on GitHub. You can download it, just follow here. So if you do have a different microcontroller within the STM32F4 family, how you can adjust your code quickly. And after that, we will use the STM32CubeMX to generate the clock parameters. Those are the parameters that are used to change the clock speed, and you need to know them correctly to update them correctly within the next part of this video, which is building the clock function. At the end, this is the STM that we are going to use. The board is called STM32F4VE. It's a Chinese board that I really enjoy. The pin structure is quite nice. They do have also specific pin for some devices, so which is quite a good board. And for the logic analyzer or the signal sampling device that we are using, today I'm using the Regal MSO5000 series. That's an oscilloscope. Okay, so if you're really interested to how to know to change the clock and understand every step of the process, this video is the video that you have to watch. Thank you, and let's start. Okay, as you can see this time also, we are having a new microcontroller, but we are using the same code we have been using all along. And this is to show that the code that we are going to make is really modular. So we do have the STM32F4 07, and this time where I will show you how to change it again. So let's quickly hide this the picture of the microcontroller. And now what we are going to do, as we have seen in the previous video, again, we go to device and we put the STM32F407 VETX. Okay, so we changed the microcontroller. Now what we are going to do, we need to go here again and go for the debug, select the ST-Link, check that everything is connected and well recognized. Check this reset and run and check that this one is not enabled. So now our code has been updated, and if you go to the clock.h for this one that we have selected, we can see that this one is now defined instead of the previous one, which used to be this F446XX. Okay, so now let's just, for sake of checking, let's build the code again. Always build the code again, so 0 error, 0 warning, and load it in the microcontroller. And let's take a look on the oscilloscope output. Okay, let me find the oscilloscope. Where's the oscilloscope? Yeah, here it is. Okay, let's read the frequency that we do have. So the MCO1, let's check here. So the D1, sorry, the D0 is the one connected to MCO1, and MCO1 is HSE, which is the external clock, and the MCO2, sorry, is the system clock. So our system clock now is 16 megahertz, where the external clock is 8 megahertz. And let's put divide by 1 just to be sure at 100% that that's the value that we do have, and bring back the oscilloscope here. So we do have here the frequency of the external clock, or the HSE, at 8 megahertz, which is exactly the level that we need. So with this one, we have integrated our new microcontroller for the readings, and this is exactly as we have seen the previous time. We have completed now the step of updating the new MCU with a clocking KEIL. We can go to the next step, and this is the one where we'll try to understand how we are going to get the change of the parameters of the clock and how we will generate them using the STM32 CubeMX. So this is the CubeMX we have been using the whole time. So let's make it bigger. But this one is for the STM F446RET. But the logic will stay always the same, and we will see that we can deploy this to many microcontrollers in the last video of this chapter of the clock. So I will go here and I will change the microcontroller selection that I do have, going here, and it will be the 407DET6 like this, and we select this one. So what we would like to have is to use that external clock because it provides more stability in the clock. And so to do so, we go to the system core RCC, and then for the high-speed clock HSE, we can say crystal or ceramic resonator. And this is the module that we do have. So I hope I can show it here. So this is the ceramic, it is exactly here. And this is what we are going to use in this one to show it. So that's exactly the one here. Okay, and again, you can find it through the spec of the datasheet, or if you do have a very simple logic analyzer, you can use it to read the data. Good, so we put that, and then if we go to the clock, we can see now that better to show you before that. So if I put disable, so you can see I'm not able to use it like this. So if I go to crystal or ceramic, I will have this one ready. So let me also hide the video here. And the first important thing to do really is to change the input frequency. This one here that we do have. So you have to change this 25 to 8 because this is the input of your crystal. Okay. After that, what you want to do is to select this input frequency as the input for the PLL, and then for the PLL clock to get your output. And interestingly enough, if those values have a problem, that will be in red, and you will see that you will start having trouble in your code. Because, for example, here, if you set like this, because of this data change and you do have the PLL, you will have a system clock of 48. And if you change just like this, when we will build the code, we will see all the steps that we need to respect before doing this change. But just to see that this can damage your microcontroller. So respecting those steps is extremely important. Okay, so you see the one in red means you do have trouble with your microcontroller or the different buses controls. So to do the correction, you just come here and put the value that you would like to reach. And we would like to unleash the beast, really giving a full power to our microcontroller, which will be 168 megahertz. By clicking this, the software here will start finding all the parameters that will be suitable at each step to make the implementation. Okay, so based on this, we can get generated a list of few parameters. So we do have the M parameters, the N, the P, the Q also. This is an important one. And after that, you do have this AHB prescaler. And after that, also you have the APB1. Let me zoom here and bring it here. So the APB1 prescaler and also the APB2. Using all those parameters, you can have a good transition or a correct transition to your microcontroller new clock speed. Okay, so now that we do have and we know which parameters we need to use to change our clock, we can start building our function. But this time I already built the function and I will explain how to set up all of them. And this is because it's quite a little bit long function. You can download it from GitHub and you can use this code immediately. But it's very important to understand every step so you can also reproduce it in other families of STM32F4 or STM32 short. Okay, so let me go to the code and bring it. So the function is called, I will start with this one first here. So this is a long function and this is done in purpose. So each time you have a change of or a target microcontroller's clock speed, you can just input those parameters and you can enjoy the flexibility and the modularity of this function. You just generate the parameters from the STM, the cube, and bring it here. You can also challenge yourself and create the function that will generate those parameters, but that's something for another time. Okay, so let's open this function and explore it step by step. So as we have seen in the previous video, we will have to deal, and let me open here. I think I do not have prepared the, I'll need to bring the code of the datasheet of the STM32F4. So let me open it right now here, and it's coming. Yes, the datasheet of, oh no, not the datasheet, the reference material. And we would like to go for the RCC. And this is where is the reset and clock control. And we go to the registers. So those one are here. And one of the challenging register to catch is the PLLN. And this one, to catch it, we need to have a specific mask. That's why this variable has been created. And after that, there's the total div. This one will be used later on, and we will see how. So first thing to do, activate the external clock input. So this is a function that we have created in the video number 1. Then we need to manage the power of the RCC. There is a power bit that we need to enable, and you can see there's some register here directly connected to this library. Those registers are predefined, so better to use them directly. You can use the number, so I can show you this one. So let me go back. Let me hide this one and hide this one and hide this one. So to go only to this speed. So we go to the APB1. So let me go for the APB1. APB1 enable register. This one. And the power, let me find it just a second. Just again, quickly. This is APB1. And the power is somewhere here. Just a moment. Yeah, I have done this and I forgot how I have generated it. Interesting enough. Not this one. Is the power connect. Probably power enable. Power enable register. Probably, yeah, because I was looking in the wrong in the wrong one. It's here, power enable 28. Somehow, yeah. Okay, so this one, and if we go for 28 here, so this one help the power stabilization or the performance of the microcontroller. And we will see later in the next video on the last chapter how enabling the power or how changing the clock speed will impact the power consumption of the microcontroller. Okay, and after that there is the flash parameters. This one is an extremely important one, so the flash clock gets sync with the clock change. You just have to copy this line and you make it. So that's just about the flash, how to get sync with the clock change. Then we go and we start the input of our parameters. So we do have two sides, and let me show it here again. So let's just a second. So the first side is whatever before the clock and then after the clock. So we are now going to take a look on every element after the clock. So here, and we are checking the clock. So the first one is the AHP1 prescaler. This is an interesting parameter. So if we go here and we go to this one again, and we go for this one. So in this one, there's a certain logic. So this is the one that we need to change here. We do have 4 bits to control, and this bit starts from, I think, I'm losing it a little bit here. And it's extremely interesting. So the 8 hexadecimal will be equal to 2, where the F hexadecimal will be equal to 512. So some logic is needed, and this is how the logic is integrated. So what we do, we keep dividing by 2 to get how many times we have a 2, and then the total div, and this is the parameter we added here, we count how many times is divided by 2, and we add 7. And this, like this, we can match directly with this one. So the user can input 2, 4, 8, or this number, something that is really meaningful and connected directly with this one. This is the AHB prescaler that we are going to input. And using this logic, so let's go back here, we can get the right parameter to input. And here we do have the AHB prescaler position. And this is a parameter I added here. This one is just to find the position within the register. Exactly the same for APB1. There is a mapping that we need to apply. The mapping is much easier here, where 4 means 2, 5 is 4, and then so on until 16. So the user will be able to add those elements here, 2, 4, 8, or 16. And then the program needs to change it. It's exactly the same logic for APB1 and APB2. So let's go back here, make this one bigger, and we will each time use the total div to count how many and then add it to the prescaler. So this is for APB1 and this one for APB2. So we add each time here 3, because let me bring it back here, because everything under 3 means there is no division. But after that, and as usual, I apply here 7 or 111 binary, because I would like to clean the prescaler before applying the number I would like to apply. Okay, so same thing for APB1 and APB2. And after that, we start the configuration of the PLL parameters. The PLL parameters, if we go back here, are all the parameters, the M, the N, the P, and the Q generated by the system that we would like to use. So we start by the first one, which is the N parameter. And we have seen in the previous session how we created this N mask. And this is to first clear that element. And I created some memory mapping here. So this is for the Q, this is for the P, this is for the N, and however, so the N mask, and here For the M, it's 0, because if we go back here and we check for the RCC configuration, not configuration, sorry, PLL configuration, the M parameters here, we don't need to shift nothing. The number is itself here connected, so there's no need to shift it. But I'm applying 3F to put the whole thing to 0. I'm putting everything to 0 before, after that, applying each one of the parameters using their position. So I'm applying the whole thing in one shot. So I applied all the parameters for the whatever the the buses, and then I applied the parameters for the PLL. Then I can start and activate. So here I'm selecting my HSE or my external clock as a source for PLL. And if we go back here for the registers and check, so if I go to PLL here and check what is my source, and this is the bit number 22, if I apply 1, means HSE is my source. Okay? And then I can activate or enable the PLL function. Okay, so I activate it. And finally, what I need to do is to run this switch. To run this switch, I'm using the code used in the library, which is RCC configuration switch to PLL. And this is doing, if I go back here, is the RCC, no, not this one, the configuration, and I'm applying it here. And applying it in a way, so if we go to the end here, I'm applying PLL as the selected system clock. And we need to keep waiting until this is activated. And when it is activated, all is good. So we do have now the whole function that we can use. Let me make it smaller, where we can input all those parameters so we can change our clock speed. Okay, so we created this one, we the function, and we have all the parameters. And here come the example that will show how useful and easy this function to make. So what I have created here is a simple function, and you can, if you have a different microcontroller and you have in mind a different frequency, you just here put the name and the frequency, and this is helping you just to map it. So, and here I'm putting just what is my microcontroller and what is the speed of, let's add megahertz here just in case, and to see how these parameters are applied. Okay, so I'm taking every parameters, the M, the N, the P and the Q, also the prescaler for the buses, exactly same as here. And I'm just applying them. So if you would like to copy, you just change those parameters, depends on your microcontroller. Okay, and I already copy paste this function here into the header file. So now what I need to do, so let's save here. What I need to do is just coming, so we don't need those one anymore. We just come here and paste here. So let's remove this void. Okay, and we do have the function that will provide us the change the speed of our microcontroller. So what we can do is to make this one smaller like this, so we can see this, see the frequencies, and let's build, save and build, 0 error, 0 warning, and then load the code. Take a bit of time. So you can see now that my frequency, the output frequency here is 166. And if I check, it's flipping between 200 and 166, and we are reading something between a cycle of 6 nanosecond, 5 nanosecond, 7 nanosecond by cycle, which is really, really good. So if I go back here to my STM and I activate my MCO1 and MCO2 just in case, and I check on my MCO2 for my system clock, it should be 168. Okay, where if I check my whatever the exit one, the HSE, the external one, it should be 8 megahertz. So now we could have the 8 megahertz as the external clock, and this is simple, and also the system clock. We could read and change the system clock. Finally, just in case, we still can use the functions that we built to understand our system clock. So if we go here and go for the debug and run it, so we can see now the PLL is 168, and actually also the system clock is 168. And doing so, we have completed a whole cycle of controlling of the clock. Good. I hope you enjoyed this episode. In the next one, we will see how we can apply the same function to other different clocks. Also build two final very important functions related to the clock change, because with great power comes great responsibilities, and also review the power consumption status that will change. Hope you enjoyed this episode and see you soon. Bye bye.